My name is Nolan Preble, and I am presenting my final project for my controls class for mechanical engineering. The chosen project is doing cruise control on a sedan. The physical system design, the actual actuator that we'll be using to control the velocity, which is the desired output and input of this system, is controlling velocity, maintaining velocity. Velocity is actually controlled by a throttle actuator, which will control the amount of fuel entering an engine, which will be proportional to how fast it goes. And the actual actuator is controlled by the gas pedal angle. And to ensure that the set velocity is maintained, we'll be using a wheel speed sensor, which will measure how fast the wheels are turning. And with that, we'll convert that into speed, which will let our sensors know how fast our car is going. The physical inputs for this system will be roads and their gradients. So if a car is going uphill, it'll be incurring gravitational force, which will slow it down. Likewise, with a negative gradient, the car will accelerate, causing it to increase speed, and where we will have to maintain a certain speed. We also have wind resistance, which increases with speed. We'll have to be conscious of that as higher speeds are maintained, and also rolling friction. But for the simplicity of this model, we'll be assuming that is a constant. Software integration. The performance guidelines to see how well we're doing is speed maintenance. We want to deviate little from the set speed with all the noise and resistance previously mentioned. We want a responsive system that will quickly take the passenger and the car to the desired speed, also at a comfortable pace. We want a little overshoot if we exceed the speed limit, so to speak. If you were to set the cruise control at the speed limit, which it often is, we would technically be breaking the law, and there are legal concerns there. The controller choice is a PID, simple PID. However, it will be software based, and it'll be connected to the ECU, which is found in the engine compartment. ECU stands for electronic control unit. And the information that's going to be fed into this PID is going to come from the wheel speed sensor. The physical model of this system, I chose to use data from a 2023 Toyota Corolla, very popular car, 1,400 kilograms. We calculate the normal force for this, and looked up common values for rolling resistance and constant and drag constant for this car. We have the input of velocity going towards the right. We have drag towards the left. And I developed this governing equation, MA equals U minus BV. It's going to be based around velocity. So I changed the acceleration variable to be velocity dot. And from there, we made so the output was the change velocity. So state variables, V equals X. I created my state space. And the drag equations, I used commonly held equations to measure how we're going to work that out. The continuous math, as far as controller tuning goes, I use PID in MATLAB and Simulink. I toggled with the different values of what I could get to get the ideal response that I would have, which is ideally for the proportional aspect, I want a larger value so we can quickly adjust to the set speed to maintain what we're looking for. I want good integral too, to make sure that there's no overshoot, so we're not breaking the law. And for a derivative, I was ideally looking for a medium value to have a smooth but quick transition. Nonlinear considerations to have is right now we're only assuming that the model moves in 2D. Of course, a much more accurate version would include it in 3D. I would have to linearize that in that case. Also, friction. There's a lot of different inputs as far as rolling resistance that we can encounter. Different materials that's rolling on, potholes, all that. And also with different speeds, the rolling friction changes. Likewise, especially with speed, the air resistance changes as well. I did add in my model an equation for that, but it'd be much better to look at the aerodynamics of the car, specifically do testing before I make any hard decisions on that. Here's my Simulink model. I view as the input speed. This comes from the MATLAB code, and then it feeds into a PID, which I calculated through Simulink and through the tuning function. And I already have I put my state space model in with my equations I already derived with the values I calculated. B is calculated based on the input. As we know that drag increases with speed. To see how it reacts to different inputs, I had velocity input noises. So I had it where the velocity was increasing to simulate what it would be like to go down a hill. And I also had the velocity slowly decrease to show what it would be like to go up a hill. And as you can see in my velocity versus time graph, there was very little deviation. So I'm very happy with those results. And as far as acceleration goes, if you look at where the actual changes in velocity were, it behaved very well. Of course, at the start, there's very high acceleration, but that was assuming it was going to 0 to 60. That's not how it behaves in the real world. So I ignore that for now. System development, some of the concerns I had is reliability. We got to make sure that across all different types of terrains and different ranges of speeds, this can hold up. Safety, it's very important to have redundancy, especially in the sensors. If one of these sensors were to break, we want to make sure that there was no buildup of speed or it's uncontrollable. And it's also very important to have these sensors be precise so the actual physical system is being modeled well. Security as well. I won't want any of these components have access to the internet where someone could hack it and manipulate it. Troubleshooting. To get a more accurate model of this, I would want to perform physical testing on the system. I also want to develop a much more complicated model of the physical system. Make sure, do a whole lot of different testing to make sure that across all the common values and common scenarios you're going to see, that it performs accurately. I also want to make sure the equipment is well maintained, have a lot of redundancy there, make sure we have sensors on the equipment to make sure to let know when it's time to replace that. And as far as automation concerns, I'd have forward car detection. You can't trust that these drivers are always competent or paying attention to the road. You'd want to have sensors in front to make sure that if a car was getting too close to another car, that it would slow down. And that is all. Thank you very much for your time.